Welcome to the Meadow Map. It's a landscape of garden plots, burrows, and stepping stone paths, where observing rabbits in their burrows or turtles crossing the stones teaches us a core rule of geometry. Picture the land, then measure it. This animated diagram outlines the mathematical definition of similarity. A shape is similar to another only if we can recreate it using a specific sequence, rigid motions combined with a dilation. We often describe similar figures as having the same shape but a scaled size. In geometry, that is a strict mathematical outcome driven by exact transformations, rather than a visual guess based on how two objects look. By defining similarity through these specific, measurable transformations, we gain a precise system to prove exactly how two geometric shapes relate to one another. Looking at this stepping stone path, we have an initial shape, triangle ABC, with exact side lengths of 3, 4, and 5. Further down the path is triangle DEF, with side lengths 6, 8, and 10. Our challenge is to prove whether these two triangles are mathematically similar. We test the relationship by checking the ratios of the corresponding sides. The math here is exact. 6 divided by 3 is 2. 8 divided by 4 is 2. 10 divided by 5 is 2. Every corresponding side length on the new triangle is precisely twice that of the original. That constant ratio gives us our first transformation step. We dilate the original triangle by a scale factor of 2. Next, we apply our rigid motions. The newly dilated triangle rotates and translates, moving into the exact position to overlap our target triangle. A dilation followed by a rigid motion successfully mapped the starting shape to the target shape. This proves the figures are similar, confirming that we can resize shapes while keeping all their internal proportions perfectly intact. Here we see a geometric polygon mapped on an exact coordinate grid, representing a fox's marked territory with specific starting coordinates and size. We start by rotating the territory. This specific rigid motion changes smaller orientation, but it strictly locks both the size and the shape in place. Then we apply a dilation by a scale factor of 1/2. This shrinks all the side lengths symmetrically, altering the overall size of the territory. Given these two moves, is the resulting territory congruent to the original, similar, or both? The final shape is similar, but it is explicitly not congruent. Congruence requires figures to be absolutely identical in size, which forbids any changes in scale. Similarity relies on that very size change. This diagram illustrates two different size triangular paths that can be mapped onto each other using a dilation and a translation. We need to see what happens to their interior angles, highlighted here with amber markers. When we dilate the first shape, the side lengths stretch, but notice the interior angles. Those angle measures remain completely undisturbed. Next, we translate the shape. The sliding motion moves the triangle into place, continuing to keep those internal angle measures perfectly locked. This demonstrates an absolute rule. In any similar figures, even if the overall sizes differ drastically, the corresponding interior angles are permanently and congruently matched. You can prove any one figure maps to another by identifying the exact dilation and rigid motions required to get there. This checklist outlines your final verification for similarity. Check for equal interior angles and verify proportionally scaled sides. Locking down this definition gives you the tools to analyze complex triangles, setting up your next step, measuring geometric slope.